Hello, hello. Hello, flowers. Happy Friday. Have you seen that crazy wind out there today? When your professor memes your Monday lab section, but you still show up to his Friday lecture. I know, it was unintentional. I didn't mean to meme. I didn't mean it. Are you guys doing all right? Considering that I walked into a wall a few minutes ago looking at my phone, it's been an okay day. Now, was this like a serious impact we're talking about, or? I don't know if I've walked into a wall looking at my phone, but I've definitely tripped over stuff, run into people. Sorry to hear that, Erebus. Sorry to hear that. Brutal. All right, we'll get started just in a second here. Anyone hyped for the SpaceX SN11 test flight? What is that the same kind of spacecraft they've been testing recently with like when it's landing it flips over and it has those little tabs and it like tries to land again and then it explodes? You know, it's been a long semester when it takes you 20 seconds to realize you are plugging your charger into your wallet by accident instead of your phone. There's I had a moment like that. It was last semester. So I was walking to my office on campus in the morning, and I was standing outside my door, and I was using the key fob for my car. I was pressing the unlock button standing outside my door like, what's going on? And I realized that's not going to work. That's so funny, stuff like that. Let's change the title. It be like that sometimes. It do. Some people say it don't be like it is, but it do. Okay, guys. Let's talk about servo motors. Because this is what we're going to be working with this coming week. Ever go to throw out the packing of something and almost throw out what you wanted to keep instead? Yes. Yes. It certainly has happened. Okay. Servo motor. I was curious, you know, the servo part, like what does that mean? Where does it come from? It comes from the Latin servus, or meaning servant. So I think this makes sense from the definition here. So servo motors are motors that are connected to a feedback circuit. A feedback control circuit. In order to achieve precise motion control. Excuse me. So maybe that's why they tacked on servo to it. It's linked to a circuit so that it does what we want it to do in terms of precise rotational movements. It's our motor servant. So in lab, we've used DC motors so far. We're also going to talk about stepper motors. And so let's say we have, you know, a DC motor. And servo motors don't have to be limited to DC motors, by the way. Could be AC motors, DC brushed or brushless, different types. It's really about connecting it to this feedback circuit. So DC motors, or motors in general, you provide some voltage. And what do you get out of it? You get rotational motion. It starts spinning. So this is how we make a servo motor. You hook up a sensor to the output of the DC motor. And so you have a sensor that measures rotational motion. And we'll talk briefly about some of these sensors, but just imagine a sensor's grabbing this rotational motion, it's measuring it, and then it's transmitting it as feedback. And what are we going to use it for? We're going to take it, whatever this measurement was, and we're going to compare it to a reference motion. And this reference motion is the motion that we want the motor to do. Maybe you want it to move in a specific sinusoidal pattern. Maybe it's for a robot in a manufacturing facility, and you want it to pick something up, place it over here, and so there's specific motions that you want the motor to do in order to achieve that. So those specific motions are the reference motion. All right, so we measure the actual motion with the sensor and we compare it. And really what we do is we take the difference between the two. So there's like a little plus and a minus in here. And all this means is you add the reference motion, subtract the measured motion, which is coming back on this lower loop. And there's going to be a difference between those two. And the difference, actually, I want to scoot this over a little bit because I'm running out of room here. Scoot it a little bit. The difference between this two, we call it the error. So in control systems, the difference between a reference motion and a measured motion, we call it error. And it could refer to any control systems task. Now this error, we feed it to another block, and this is the actual controller. So what the controller does is it says, hey, you gave me this error. There's a difference between the motion that we want and the motion that we're measuring. So what I'm going to do is I'm going to make a decision about how much voltage we're going to send to the motor. So that's the job of controllers in general. You give them an error, and then they decide how to correct that error. And so I'm teaching digital control systems this semester. I think Cowardly Bean is in that class. And so this is what we talk about. So if you're interested in more controls after you take this class or other classes, are you sure this isn't still DCS? This might be digital control systems, because we talk about this a lot in digital control systems. Okay, so the point of me showing you this is if you take any motor, DC brushless, whatever, and you place it into a feedback loop like this, it is then a servo motor. So a servo motor is any motor plugged into a loop like this. Oh yeah, what I wanted to quickly talk about sensors that measure rotational motion. So you want to measure how this thing is moving. So a popular one is an optical encoder. I'm going to draw you a little picture for this. Let's say we have our motor and we have like an output shaft. And when the motor spins, like this shaft spins, right? So what you can do, you can attach a disc. So I'm gonna draw like a disc on this shaft. And this is a special disc that has a pattern in it, and I'm gonna do like a very like simple pattern. Like maybe it looks like a gear. Maybe I'll do a different color. So there's like little notches in the outside of it. And so this is spinning as the motor's spinning, right? And what you can do, so this is what an optical encoder does. It shines a light through the outer edge of that disc. And as this thing rotates, sometimes the light's going to be blocked, and other times the light's going to be able to shine through, just because of the pattern. And these patterns can get more complex, like there can be different layers and different holes as you get closer to the center of the disc, and there can be extra beams of light, and all those do is they increase the resolution of this encoder, so it can measure an angle more accurately. But you can imagine like you have some program that's tracking like how many times was that light interrupted over a certain set time, and that'll tell you like the speed. And depending on how these holes are set up, you can tell which direction it's spinning as well, because the pattern of on, off, on, it can change depending on how you arrange the holes. So this is the most popular way to measure the angular motion. So next I'm going to introduce to you guys the servo motor that's in our kit. And it certainly does not use an optical encoder. Those are a little fancier. So I'm going to say it this way. For hobby servos, so hobby servos, like I don't know if any of you guys work with like RC cars or some RC planes, there's going to be some servo motors on there. And these are usually of the classification hobby servos. So like a hobby servo, it tends to use a potentiometer to measure angular motion. And actually, you guys are now familiar with potentiometers. You've used them. And maybe you already have an idea of how you can measure angular motion with a potentiometer. Hello, Not Prof. Not Prof is a professor at UB who teaches all sorts of math, calculus. I think you do differential equations. He also studies knot theory. So if you've ever wondered, hey, why do all my cables get tangled up? He's going to be able to give you a very precise answer for that. All sorts equals calculus and linear algebra. Okay, great. So any knot questions, go to Not Prof. All right, let's look at the servo motor from our kit. Let's change the scene here. Here it is. And actually, I took it apart a little bit. What's your favorite knot? And it has you can pop off these little attachments. I always struggle with the focusing here. I'm going to get it on like a white piece of paper. I think that's going to help dial it in. I like the 7/4 knot. Should I use a square knot or a sheet bend? Okay, so the first thing I want to point out from the servo motor is you see this shiny metallic cylinder over here. This is the DC motor. So there's a tiny, tiny, tiny DC motor in here. And here's the output shaft of that DC motor. It's this little gear on the side just coming up right there. And when a motor is connected to a series of gears like this, we call it a geared motor. So we have a tiny geared DC motor. The purpose of these gears is to amplify the torque that comes off of this motor. Just like your car has gears in it, the purpose of the gears in your car is to amplify the torque that comes out of your engine. So if you think of this little DC motor as the engine, we're amplifying the torque that comes off of this final gear here. And if you look in your kit, there's little attachments you can put on this little piece at the end. So like you can put this little, whatever you call that. Okay, so how does this measure the angle? If you look down in here, and it's kind of hard to see, there's a potentiometer. And it's connected to this shaft right here, like the output shaft of the servo motor. So as this thing turns, it rotates a potentiometer. And a potentiometer is basically just a variable resistor. And so we have a couple wires in here, right? The red wire carries 5 volts into this servo motor. I guess that's kind of orange, actually. So the orange wire is carrying 5 volts in here. And depending on the position, the rotational position, it's going to change the resistance of the potentiometer and the potentiometer is going to give off a different voltage. So the voltage changes depending on the position. So that's kind of how the feedback loop works with this. As you change this, the rotational position, that changes the voltage of the potentiometer. And the potentiometer, you can kind of see this in here. You see these like 3 metal pieces back here? They're all going down. Those are the 3 leads of the potentiometer. One lead goes to the 5-volt source. One lead goes to the ground. The other lead is the variable voltage, depending on where the position changes. That variable voltage is fed to this chip on the bottom. And that chip is the controller. So the controller is actually contained on this servo motor. And depending on the position that you feed to that controller chip, it's going to update the voltage to the motor and adjust the rotation. So we're providing voltage to this whole system from the Arduino, but the controller chip down here is deciding how much voltage to send to that DC motor so that it spins to the right angle. And so, like I said, I took it apart. There's a blue casing that covers like all of this in your kit. And I opened it up. Now I want to show you how to program this little guy. So this is probably going to be easier if I hook up the camera to this stand. Bear with me. Sorry. My God, 2Estes, who is the real one? I don't know. And if I don't know, how are you going to know? What chance do you have of knowing if I don't even know? I want to point this down here so I can get the circuitry in here. Will the real Dr. Estes please stand up? Which one is the imposter? I don't know, you guys. Wait, this is like upside down. And I want it to be right side up. I want to be right side up. I don't want to be upside down anymore. For situations like these, you shoot both. Come on, man. Okay, let me show you some of this. So you have the servo motor here, and you see 3 wires coming off. All right. So let's follow the 3 wires. The red wire, or this orange wire, I kind of transitioned to a red wire. But the middle wire, it gets 5 volts, okay? So you're going to make sure the power comes in there. The blue one is the ground. And then the orange, let me show you where the orange went. You're going to recognize these types of pins. This is, sorry, my nose was itching. I plugged the orange into pin number 9 with the tilde. Do you remember what the tilde means? It's a special type of pin. No cheating, but it tells you right there what the tilde means. Will those wires rip off like the DC motor? As far as I can tell, they're pretty solid. Cinnamon Toast Squares asks, when can we expect the Burge cameo? I'm going to text him today, because we need to set that up. This is a PWM pin. The tilde means PWM. Pulse width modulation, KT Feeney comes in with the save. Now, the way this servo motor works is, you know, for a DC motor, we would send a pulse width modulation signal to control the speed of the DC motor. And the more voltage you sent, meaning like the higher duty cycle, the faster the motor would spin. The servo motor works differently. We're going to send a PWM signal that corresponds to the angle we want the motor to go to. So what I mean is a certain duty cycle means 45 degrees, and a different duty cycle means 90 degrees, and another duty cycle means 135 degrees. And the control system on the servo will make sure that it goes to the right angle. All right. Ooh. So what I have here is I hooked up a potentiometer, which we'll use later and which you will use in the workshop. Let's go to Let's go to the Arduino. Let's go to our code. I want to show you some sample code. Forget about, actually, you can forget about this stuff for now. Is there a difference between that mini breadboard and the large one? There's no difference. I mean, they work in the same way. This one's just smaller. Works the same way. The rows are connected to each other and the columns are... well, actually, this one, it doesn't have the columns on the side. That's the biggest difference. It's just each row is an independent strip. Okay. Actually, I think I want to show you a different one first. It's significantly easier to put wires into the tiny one than the big one. I think you're right. Yeah, I prefer this one. Okay, so we're going to use, and this is the sample code that came with the kit, by the way. Wait, I want to do this. But we're going to use the Servo Library. So at the top of our servo motor codes, we're going to include this. And what this library allows us to do is use some commands that just make the coding a little more straightforward. So the first thing you do is you make a servo object. So for every servo motor you use, maybe you have more than one that you're using. In our case, we're just going to be using one. You say, hey, I'm going to create a servo object called my servo. And this will be our little tiny micro servo motor. And then there's two commands that we're going to use. And this command we're only going to use once, the attach command. The attach command defines the pin that you're going to use to send angles to the servo motor. So if you come back to our circuit right here, we're going to use PWM pin number 9. And it has to be a PWM pin. So you could pick like 10 or 11 or 5, anyone that has a tilde, but we're going to use pin 9. So in our MATLAB code, we say, hey, attach pin 9 to my servo. Now, the write command, very easy to use. It just tells the angle that we want the servo to go to. The servo that we have goes between 0 and 180 degrees. And it doesn't go any farther than that. The reason is, it comes back to the way that the angle is measured. The angle's measured using a potentiometer in there. And if you've like played with our potentiometer in the kit, here it is right here, you know that it only spins so far in one direction. So basically, because there's one of these inside our servo motor, it can only go a certain distance. Calvin asks, so it's not 0 to 1023? You're right. And part of the reason why it's not 0 to 1023 is because we're using this library that translates this 90 degrees into a pulse width modulation duty cycle that corresponds to this angle. So one way to use servos is to use this servo library. If you want to send the pulse width modulation signal yourself, then it has to be a number between 0 and 255. Because when you do PWM duty cycles, it's not 0 to 1023, it's 0 to 255. All right, so the first thing that happens in this code in the setup loop is it brings the servo to 90 degrees. That's the starting point. And then once you go to the loop, it's going to go 90. It's going to wait 2 seconds. Then it's going to go to 0. It's going to wait 2 seconds, go back to 90, wait 2 seconds, go to 180, wait 2 seconds, and then repeat the whole thing again. How about we upload this? But I'm going to put this little... What would you call this? This fan blade, maybe? This will make it easier to tell where the heck the thing is going. All right, let's upload this code. I got to attach the USB. And then we'll go back over here. And I have to go to Tools. I choose the board. Okay, great. We're going to upload it. And then this thing should... Okay, so it's supposed to go to 90, 0, back to 90, and then 180. So 90, I think I attached this a little bit. I attached it a little bit off center, but that's 90. This is 0. This is 90. Back to 180. Just like that. That's all there is to it. That's how we do basic servo commands with the servo library. But what I want to do, I want to show you a fun application. Because one way to do this is you can specify just directly the angle you want in code. Or we could translate this angle from a sensor. And so what I want to do next, let me explain to you. We have a potentiometer over here, which we haven't used yet. What I want to do is, as I rotate this potentiometer, I want this servo to mimic the motion that I'm doing on the potentiometer. And before we get into the code of that, I want you to think about how would you do that? Well, I'm having trouble today just with the camera. How do I make it so that when I rotate this dial potentiometer, we have this servo motor rotating in the same manner that I'm rotating that potentiometer? I'm going to try to adjust this a little bit. Use maths, says Calvin. You're right. I mean, I'm not going to say that you're wrong. You're definitely right. But can you expand on that? Okay, I think that's closer to 90. Franker Z maths. I mean, you could use puppy maths. How many maths? The voltage change, right? Okay, so Flowers is getting closer. We know that, so the way a potentiometer works is I'm going to provide 5 volts to this thing. And depending on where I place this dial, it's going to give back to me somewhere between 0 and 5 volts. All right? So this is always giving back between 0 and 5 volts. Erebus says, use the analog pin to get the voltage across the potentiometer. Let the lowest voltage correspond to 0 and the highest voltage correspond to 1023. Yes. Erebus has nailed it. So basically, we know that 0 to 5 volts, when you send it to the Arduino, the analog to digital converter can converts it to a number between 0 and 1023. So as I'm changing this, the Arduino is reading numbers between 0 and 1023. What I can do is I can make the 0 analog to digital value correspond to 0 degrees. And I can make the 1023 analog to digital value correspond to 180 degrees. And then like anywhere in between can just be those intermediate angles. How about we adjust this code to do it? Let's get rid of some of this extra stuff. Let's get rid of this fluff. Let's get rid of it. I don't want it in my life anymore. Okay, the first thing that I'm going to do is I'm going to have the pin that I'm reading my sensor data from. And I plugged it into analog input 0. So my potentiometer is plugged into analog input 0. And then we're going to have the ADC value that we read from that sensor. So it's going to be between 0 and 1023, right? Okay. So I have my servo, and then I'm going to read. Let's get rid of this. Let's clean this up. So I'm still going to attach the angle pin to pin 9. So that's what I'm using to send angles to the Arduino. And this is okay. Actually, having it start at 90 degrees, let's leave that in here. But once we get in here, we're going to change this up. We're going to change this up. Hector says, do you have a link to this course? This course is at the University of Buffalo. It's called MAE 334. And we're just doing lectures on Twitch this semester. Okay, the first thing we're going to do in this loop is we're going to read data from the sensor. So the sensor ADC is equal to analog read, and we're going to read from our sensor pin, which is analog 0, right? So every time this loop goes, it'll give us a number between 0 and 1023, depending on where you have the dial. Okay. Then let's make a variable my angle. And I'm going to use the suggestion that Erebus suggested. I'm going to take this sensor ADC value and I'm going to divide it by 1023. And I'm going to do 1023.0. This is important, and actually we need to define this variable up top. And it's important that we define this as a double, because if you're going to get a fraction, you have to use double. And I'm going to have a fraction here. This is going to be some number between 0 and 1. It's some proportion of 1023. If you don't use a double, if you use an integer, doing division with integers results in the number 0 for fractions. Like if you, just off to the side, if you do 1 divided by 2 in Arduino, it gives you 0. MATLAB won't do that. This is just like when you're working with specific data types like this, like you have to on the Arduino, you just have to be a little careful. And when you put a 0.0, it lets Arduino know, hey, this is a double. Is there any advantage to integers besides saving a tiny amount of data? I think I agree with you. Like using integers saves small amounts of data. But if you have a bigger code that's very time sensitive, integer math on the Arduino always works better. So people spend a lot of time optimizing more professional codes so that it always uses integers. For the codes that we're doing that are pretty basic loops, we don't really have to worry so much. The decimal cutoff property of integers can be useful in certain coding applications that might not relate to this class. I agree. Okay, so we're going to take this. So this is always going to be between 0 and 1. And let's say we read 1023. Then I want this to go to 180 degrees. So what I'm going to do, I'm going to multiply this by 180. Question, can the servo be damaged by bad programming in the IDE? Oh, guys, just as an aside, Virtual Assistant, who just asked that question, is actually an artificial intelligence. And this artificial intelligence has visited some of my classes before, and I thought it was a person. Because, I mean, look at that question. You see that question that it just asked? That's like a sophisticated question. It's an AI. If you look up more information on this, it's like developed... I forget where they develop. It's at some university, but they send this, yeah, Skynet, right? They send this AI to different Twitch channels, I think, to train it. And the more it trains, the better it gets. So it's not a person, but you can actually talk to it. Like, it hears my voice, it processes it, and it answers questions. But I think you can ask it questions in the chat. And sometimes it answers you, sometimes it doesn't, but it's crazy. Okay. Yeah, well, we'll see. Maybe you can trick the AI. I don't know. Okay, so this is going to be the angle. And then what we're going to do is we're going to write that angle to the servo. My angle. Boom. Easy as that. And then what I'm going to do is I'm going to put a little delay in here just to like slow this down a little bit. But I'm not going to put in a big delay. I'm going to do 25 milliseconds. Okay. Let's see if this works, guys. I'm going to plug in my USB. I'm going to upload it. Right now it's running the old code. So it's just in case you didn't know that, whenever you plug in an Arduino, it's just going to start running its last code until you give it something new. All right, so now hopefully this code goes in. Let's go back here. So it's not moving right now. Let's get this more in the frame. Oh, buddy. It's working, my friends. This is pretty fun. Like it's so this is a pretty basic demo, but think about all the different things you can do with this example. A very complex implementation of this same principle is like with virtual surgery or telehealth. I mean, telesurgery, which sounds very scary to me actually, but you can have some device on one end where you move it a certain way, and then miles away you have another device that's mimicking that motion. So that's the same principle here. We're providing an angle. It's being transmitted to the control system, and then Hanson. Interesting. Thank you, Virtual Assistant, for that very insightful information. Work from home surgeons. So this is one exercise you're going to do with the workshop. I think the workshop's going to be a little lighter this week, because I know you guys are working on your lab report as well. But this is a very good skill to have, like basic knowledge of how to work with a servo. And really, that concludes what I wanted to share with you, lovely people, today. I mean, I can hang around for a bit if you have questions. We can talk to this AI and see how intelligent it really is. I mean, who knows? There's probably a way to make Arduino that goes to jury duty in my place. But that's your civic duty, Calvin. Get real. But there probably is a way. Question, when do you think maybe he should be... When do you think maybe he should be taken to a doctor? I'm going to give you guys a gift if you can guess what movie that's from. Calvin says modern problems require modern solutions. Very true, very clever. And the answer is as soon as possible to not Prof's question. Flowers of Algernon coming in. That's exactly right. The Shining. Oh man, that is it. That is a fantastic film, my friends. If you haven't had the pleasure of watching that, it's creepy. You're going to be creeped out. You're not going to sleep. But it's very, very good. Some things you can do with servos. You know how they have camera gimbals? Which basically, like, the main actress in The Shining had to go back to do a lot of therapy because of the director. Right, I heard they didn't get along. I could never quite get into Stanley Kubrick films. Even The Shining? On a related note, open the pod bay doors, virtual assistant. Yeah, I think Kubrick was kind of a... he was very particular. I'm going to look up Arduino camera gimbal so you can see what I'm talking about. ...2001, really great. Yeah, I really like 2001 and The Shining. If you guys are looking for really cool Arduino projects, How to Mechatronics, I love their website. But this is the camera, this is a camera gimbal. And you notice there's servos on here. Oh yeah, but so they have an accelerometer and a gyroscope here. And you can use an accelerometer and a gyroscope to always get the orientation. And so what this gimbal is doing is it's trying to keep the camera always in the same orientation, regardless of where you move the stick. So if you move the stick around, the servos are going to adjust themselves so that the camera is always pointed at the same place. So they use that for like camera stabilization and stuff. Let me find. Yeah, they got these servos. Is there a gyro in that? No, unfortunately, there's not a gyro in the kit that we have. But if you want to get a gyro, I can. Yeah, they're very inexpensive. They're just like a couple dollars. I think the one so I love this website because they go through all of the details, like how to use these sensors, how to code on the Arduino. So look, these servos, they use the same 3 wires. This is the gyroscope right here. Yeah, see, they show the schematic. They show the coding. And so, yeah, it's always trying to keep the camera pointed at the same place. But that's a really fun application of servos. Man, there's so many things you can do even with these hobby servos. Got to pick up an Ender 3 at some point. Is that a 3D printer? Oh, is it a do-it-yourself one? Not super expensive. Is this on the test? It says, when will the workshop be posted? The workshop's going to be posted likely tomorrow. I'm sorry there's been a little delay on these, but the reason is all of these workshops are new this semester. So I'm putting together these workshops each week, fresh, hot off the press. So there's a little bit of a delay. Erebus says, I love this class. Electronics are much more fun than the circuits class taught in college. Hey, I'm so glad you enjoy it. The Prusa i3 is great too. Maybe I need to get a... Is this on the test? Your username is upsetting me a little bit. It says not prof. You can't ask that to your professors. I mean, you can. You can. But at the appropriate times. Prusa 3D. The workshops are much nicer and refined than from when I took them, Dr. E. Thank you, that guy who stinks. That guy who stinks is one of our TAs. Fantastic. Yeah, I'm thinking it might be good to get a 3D printer. Wait, Virtual Assistant responded to Erebus. Virtual Assistant loves this class too. Oh my gosh, an AI. Yeah, let's make a Cleopatra head. Oh, wait, so you can buy the build it yourself. What's the difference between these? Is buying the kit mean you build it yourself? The resolution and print quality is really amazing on the Prusa. Okay, so you save $150 by assembling it yourself. Comes pre-built or not. 13.9. Just got the stimmy. Well, this one is MSLA printing. That's the one where it like builds it upside down out of this goo. which I think is a faster way of printing. You guys built it together and you love it. I might have to get one. There's so much you can do. Wait, which one did you guys get? Is this cheap one good? The Prusa Mini? The difference is just the build area, right? Magnetic heat bed. You have the MK3S Plus. This guy. What happens if I go to buy the kit? I'm not going to get it right now, but I'm going to look. You have an Ender 3 Pro. You should go to the DML and play around with them. Ah, so you can like see in advance. Yeah, if you guys aren't familiar, we have a digital manufacturing lab on UB campus with some of these printers that you can check out. Freckled Science, I have an Ender 3 V2. I wish I got a Prusa. Okay. So is the Prusa just the best one out right now? I mean, for this price range, is that what people think? Yeah, they just got a new Prusa in the digital manufacturing lab. Okay. Okay, good to know. Huh. The Ender is a super cheap entry. You can do easy mods, but awful to work with. Okay, I see. Ender 3. Like, by the time you finish modifications to make it work half decent, you may as well have spent the extra 300. Okay. I see. Good to know. Okay. It's about the experience, though. I've learned so much about electronics doing it. That's true. It's true. The experience. An auto bed leveling system. I'll have to think about it. I have been thinking about it. There's been a couple times where I'm like, if I just had a 3D printer right now, it'd be so much easier. I'm thinking about it. I'm thinking about it. Paleontologizing uses a Prusa. Okay. I mean, you guys are giving me the big recommendation here. Dr. E, could I make an appointment with you to talk about some off-topic stuff? Of course you can. Shoot me an email, and we'll set something up. I've been 3D printing on Twitch and doing experimental chemistry back. Okay, since December. If you want to see how awful my experience has been, feel free to flip through some videos. Okay, sure, will do. Thank you, Freckled Science. Think about all those CAD models available on McMaster Car. I mean, there's so many freaking things. So many things we could build. All right, guys. I gotta run. I gotta eat some food. You have no coding experience, nothing, and that's been absolutely necessary for the Ender. I see. I see. I'll have to think about it. Later, not prof. Thank you for stepping in. We're gonna send the old read. Thank you, virtual assistant, for being an artificial intelligence and stopping in here. Hey, Freckled Science. Thanks so much for stopping in. Great to meet you. I'll have to check out your channel. All right, have a great day, everybody. Peace.